Welcome to our channel with new interesting episode. Volcanoes can be active for hundreds of thousands of years, and they can erupt without warning. Recently, the Mount St. Helens Volcano alert system detected a massive increase in activity, making everyone anxious. This sudden surge has raised concerns about the stability of the volcano and the potential for a major eruption. What exactly is causing this dramatic increase? Are we on the verge of another catastrophic event? Let's explore the details and uncover the hidden threats beneath Mount St. Helens. Since early June, there has been a significant spike in seismic activity around Mount St. Helens. The number of earthquakes has sharply increased, causing widespread concern among scientists and officials. The frequency and intensity of these tremors have raised fears about the potential for a major volcanic eruption. The surge in seismic activity began with a series of small earthquakes, which were initially considered normal since Mount St. Helens frequently experiences seismic activity. However, as days passed, the number and intensity of the earthquakes increased dramatically. By mid-June, the area was experiencing dozens of tremors each week, some strong enough to be felt by residents and visitors. Mount St. Helens, known for its turbulent past, is making headlines again. Historically, the volcano experiences about 11 minor earthquakes per week, but recently this number has skyrocketed to around 35 per week. This sudden increase has captured the attention of both scientists and the public. The U.S. Geological Survey, USGS, has been closely monitoring this increase in earthquakes. Their findings indicate that these quakes are caused by magma moving beneath the volcano, a key sign of volcanic activity. This suggests that Mount St. Helens is going through a significant period of unrest. Dr. Michael Poland, a scientist at the Yellowstone Volcano Observatory, provided insights into the situation. While Mount St. Helens is known for frequent seismic activity, the recent increase is unusual. The data shows that magma is moving into the volcano's shallow magma chamber, located about 2.2 to 4.3 miles below the surface. This movement is likely causing the increased earthquake rate. Dr. Poland noted that episodes of similar unrest have occurred at Mount St. Helens approximately every 5.5 years. These episodes are not uncommon and do not necessarily mean an eruption is imminent. Another expert, Dr. Seth Moran from the USGS Cascades Volcano Observatory, emphasized the importance of monitoring changes in volcanic behavior. He stated that while the recent increase in earthquake activity is noteworthy, it doesn't mean a major eruption is imminent, as the magma is still too deep to pose an immediate threat. The USGS uses various monitoring techniques to keep a close watch on Mount St. Helens, including seismic sensors, ground deformation measurements, and gas emission analyses. Ground deformation, caused by magma moving into a volcano's chamber, is a key sign of volcanic unrest. However, there has been no significant ground deformation observed at Mount St. Helens, suggesting that magma is not moving to very shallow depths. In addition to seismic activity and ground deformation, scientists monitor gas emissions from the volcano. Changes in gases like carbon dioxide and sulfur dioxide can indicate magma moving closer to the surface. So far, there have been no significant changes in gas emissions at Mount St. Helens. While the increased seismic activity is significant, experts agree it does not currently pose a significant threat. Continuous monitoring and research are crucial to understanding the processes at work and providing timely warnings if the situation changes. The magma chamber beneath Mount St. Helens plays a central role in its volcanic activity. This chamber, located about 2.2 to 4.3 miles below the surface, accumulates magma over time. The current increase in earthquake activity is due to magma moving into this chamber, causing fractures in the surrounding rock. Despite the increased activity, experts believe a new eruption is unlikely in the near future. Dr. Michael Poland explained that the magma is still too deep to reach the surface anytime soon. For an eruption to occur, the magma would need to move much closer to the surface. Dr. Seth Moran emphasized that episodes of increased seismic activity and magma movement have occurred at Mount St. Helens before and do not always result in an eruption. The current activity is significant, but it must be viewed in the context of the volcano's long-term behavior. Mount St. Helens has a history of episodic unrest, with significant eruptions occurring in the past, such as between 2004 and 2008. These eruptions were preceded by increased seismic activity and ground deformation, similar to what is happening now. However, many episodes of unrest do not lead to eruptions. Scientists also monitor the depth of the magma. Currently, the magma is at a depth of about 2.2 to 4.3 miles, too deep for an eruption to occur. For an eruption to be likely, the magma would need to move into a smaller chamber located about 1,900 feet below sea level, providing a clear pathway to the surface. As of now, there is no evidence that this has happened. In addition to seismic activity, ground deformation, and gas emissions, scientists closely monitor the situation to provide timely warnings. Continuous monitoring is crucial for understanding the volcano's behavior and ensuring public safety. Comparing the current situation to past events, Mount St. Helens is infamous for its catastrophic eruption in 1980. This eruption, one of the most significant volcanic events in U.S. history, followed 2 months of increasing seismic activity and steam venting. A magnitude 5.1 earthquake triggered the eruption, causing a massive landslide and a lateral blast that devastated the surrounding area. The 1980 eruption caused widespread destruction, killing 57 people and causing over $1 billion in damage. The eruption created a new crater and significantly altered the landscape. Since then, Mount St. Helens has experienced intermittent activity, with a series of smaller eruptions from 2004 to 2008. Mount St. Helens has a long history of volcanic activity, with significant eruptions occurring over the past 1,000 years. The volcano has erupted numerous times, creating layers of lava, ash, and pyroclastic material. Understanding the long-term patterns of Mount St. Helens helps scientists interpret current data and assess potential risks. Despite its catastrophic eruption in 1980, Mount St. Helens has become a remarkable case study in ecological recovery and resilience. The landscape's recovery has been surprisingly rapid, showcasing the power of nature's ability to heal. After the 1980 eruption, the area around Mount St. Helens looked like a moonscape, covered in grey ash and fallen trees, with no sign of life. However, within a few years, the area began to recover. Plants started growing, and animals returned, marking the start of an ecological resurgence. One of the most significant signs of recovery is the regrowth of vegetation. Pioneer species, like lupins, were the first to take root in the ash-covered terrain. These plants helped stabilize the soil and created conditions for other species to grow. Over time, a diverse array of plants re-established themselves, transforming the barren landscape into a thriving ecosystem. The return of animals has been equally impressive. Small mammals, insects, and birds were the first to come back, followed by larger animals like elk and deer. This recovery has given scientists a unique opportunity to study how ecosystems bounce back after a major disturbance. Ongoing research at Mount St. Helens continues to uncover fascinating insights into ecological recovery. One area of focus is Spirit Lake, which was dramatically altered by the eruption. The landslide that came with the eruption filled the lake with debris, raising its bed and changing its ecosystem. Researchers have been amazed by how quickly life returned to Spirit Lake. Within a few years, bacteria and microbes colonized the lake, followed by plankton, insects, and eventually fish. A particularly interesting mystery involves the rainbow trout in Spirit Lake. These fish have grown much larger than usual, 3 times faster than trout in other lakes, but they also die young, with most not living beyond 5 years. Scientists are still investigating why this happens. Another intriguing aspect of Spirit Lake's recovery is the floating log mat. Tens of thousands of trees uprooted by the blast still float on the lake's surface. These logs create unique habitats for insects and plants, adding to the lake's biodiversity. The log mat also affects the lake's physical properties, like light penetration and temperature, influencing its ecological dynamics. The increased volcanic activity at Mount St. Helens has significant implications for local residents and emergency preparedness. The 1980 eruption highlighted the need for effective monitoring and rapid response plans to minimize the impact of volcanic events on communities. Today, advanced monitoring systems track seismic activity, ground deformation, and gas emissions. These systems provide real-time data that help scientists and authorities assess the risk of eruptions and issue timely warnings. The goal is to ensure the safety of residents and visitors by providing accurate information and guidance on potential hazards. Local communities are also involved in emergency preparedness efforts. Regular drills and public education campaigns aim to raise awareness about volcanic risks and teach residents how to respond if an eruption occurs. These initiatives are crucial for minimizing the impact of volcanic activity on human life and property. The recent increase in seismic activity at Mount St. Helens reminds us of the ongoing need for vigilance and preparedness. While the current activity does not indicate an imminent eruption, it underscores the dynamic nature of the volcano and the importance of continuous monitoring and research. Mount St. Helens has shown remarkable ecological resilience following the 1980 eruption, and ongoing research continues to reveal new insights into recovery processes and the unique dynamics of the transformed landscape. For local residents, the increased activity emphasizes the importance of preparedness and effective monitoring systems to safeguard their communities. This situation highlights the advanced technological systems used to monitor the increased seismic activity at Mount St. Helens. These systems are crucial for ensuring public safety and understanding the volcano's behavior. The Volcano Alert System at Mount St. Helens is designed to provide timely warnings about volcanic activity. This system uses a range of monitoring techniques to track changes in the volcano's behavior and assess the risk of an eruption. The alert levels range from green, normal, to red, warning, indicating increasing levels of concern and necessary actions. Currently, Mount St. Helens is at a green alert level, meaning the volcano is in a normal, non-eruptive state. Despite the recent increase in seismic activity, there have been no significant changes in ground deformation, gas emissions, or other critical indicators suggesting an imminent eruption. However, the situation is closely monitored to detect any signs of escalation. Monitoring Mount St. Helens involves various advanced tools and methods. Seismic sensors around the volcano detect earthquakes and their magnitudes, providing real-time data on seismic events to help scientists understand magma movement beneath the surface. Ground deformation is another key indicator of volcanic activity. GPS stations and tilt meters measure changes in the volcano's shape, indicating magma intrusion. For example, if the ground swells, it suggests that magma is moving into a shallow chamber, which could precede an eruption. Gas emissions are also closely monitored. Instruments measure levels of gases like carbon dioxide and sulfur dioxide released from the volcano. Significant changes in these emissions can indicate magma moving closer to the surface. So far, no major changes have been detected at Mount St. Helens, supporting the assessment that an eruption is not imminent. In addition to gas emissions, remote sensing technologies like satellite imagery and drones provide additional data on the volcano's surface conditions. These tools can detect thermal anomalies, changes in vegetation, and other surface features that may indicate volcanic activity. The combination of these technologies allows for comprehensive monitoring and a better understanding of the volcano's behavior. Based on current data, scientists do not expect an immediate eruption at Mount St. Helens. The magma is still too deep to pose an immediate threat, and there are no significant changes in other critical indicators like ground deformation or gas emissions. However, the increased seismic activity suggests that the volcano is experiencing a period of unrest, which could evolve in the coming months and years. Scientists will continue to monitor the volcano closely, looking for any changes in seismic activity, ground deformation, and gas emissions that could indicate a shift in the volcano's behavior. If the magma moves into a shallower chamber or other significant changes occur, the alert level could be raised, and appropriate measures would be taken to ensure public safety. Long-term predictions are more challenging, but historical patterns of Mount St. Helens provide some context. The volcano has experienced periods of increased activity approximately every 5.5 years, and not all these periods have led to eruptions. By studying past events and current data, scientists aim to improve their predictive models and enhance their understanding of the volcano's behavior. The technological monitoring of Mount St. Helens is a sophisticated and multifaceted system designed to provide early warnings and ensure public safety. While the current alert level remains at green, the recent increase in seismic activity underscores the importance of continuous monitoring and research. By leveraging advanced technologies and studying historical patterns, scientists can better predict future events and mitigate the risks associated with volcanic activity. Understanding past seismic events is crucial for interpreting current activity and predicting future behavior at Mount St. Helens and similar volcanic regions. 3 significant seismic events: the Hebbon Lake earthquake of 1959, the 1985 earthquake swarm, and the 2008 to 2009 Yellowstone Lake swarm, offer valuable insights into the dynamics of volcanic and seismic activity. The Hebbon Lake earthquake, which occurred on August 17, 1959, was one of the most powerful earthquakes in the region, with a magnitude of 7.3. The epicenter was near Hebbon Lake in southwestern Montana, just outside Yellowstone National Park. The earthquake caused significant ground shaking, landslides, and surface deformation. One of the most dramatic effects was the creation of Quake Lake, formed when a massive landslide dammed the Madison River. The impact of the Hebbon Lake earthquake was profound. It resulted in 28 fatalities and caused extensive damage to infrastructure, including roads, bridges, and buildings. The event highlighted the seismic volatility of the region and underscored the importance of earthquake preparedness. From a scientific perspective, the Hebbon Lake earthquake provided valuable data on fault mechanics and ground deformation. It also prompted increased monitoring and research in the Yellowstone area, leading to a better understanding of the region's seismic hazards. The event emphasized the need for robust infrastructure capable of withstanding significant seismic events and informed future strategies for earthquake response and mitigation. Building on the lessons learned from the Hebbon Lake earthquake, the 1985 earthquake swarm at Mount St. Helens was one of the most notable seismic events in the volcano's recent history. Over 3 months, more than 3,000 earthquakes shook the area, causing concern among scientists and the public. Most of these earthquakes were relatively small, but their sheer number and frequency were unprecedented at the time. The swarm began in mid-May and continued through August, with a majority of quakes occurring at shallow depths beneath the volcano. This intense seismic activity was closely monitored by scientists, who noted that the earthquakes were likely caused by magma movement within the volcano. However, despite the alarming number of quakes, the swarm did not lead to a significant eruption. The 1985 swarm provided critical data that helped researchers better understand the relationship between seismic activity and magma movement. It also highlighted the importance of continuous monitoring and the need for advanced seismic networks to detect and analyze such events. The insights gained from this swarm have been instrumental in refining predictive models and improving the accuracy of volcanic forecasts. The 2008 to 2009 Yellowstone Lake swarm was another significant seismic event in the Yellowstone region. During this period, over 900 earthquakes were recorded in the northwestern part of Yellowstone Lake. The strongest of these quakes was a magnitude 4.1, felt by many visitors and staff in the park. This swarm drew considerable attention because it occurred near the Yellowstone supervolcano's magma chamber, raising concerns about potential volcanic activity. However, scientists concluded that the swarm was likely due to the movement of hydrothermal fluids rather than magma. The rapid increase in pressure from these fluids caused fracturing in the rock, leading to the observed seismic activity. The 2008 to 2009 swarm was significant for several reasons. It demonstrated the complex interplay between hydrothermal systems and seismic activity in volcanic regions. It also underscored the importance of distinguishing between different causes of earthquakes to accurately assess volcanic hazards. The data collected during this swarm has been used to enhance monitoring techniques and improve the understanding of Yellowstone's geothermal dynamics. The lessons learned from these past events are invaluable for current and future monitoring efforts. The Hebbon Lake earthquake highlighted the need for earthquake preparedness and robust infrastructure. The 1985 earthquake swarm at Mount St. Helens emphasized the importance of continuous monitoring and advanced seismic networks. The 2008 to 2009 Yellowstone Lake swarm underscored the complexity of volcanic and hydrothermal systems and the need for accurate interpretation of seismic data. By studying these events, scientists can better predict and respond to volcanic and seismic activity. The insights gained help refine predictive models, improve monitoring techniques, and enhance public safety measures. Understanding past events is crucial for mitigating the impacts of future seismic and volcanic activity, ensuring that communities are better prepared and informed. Thanks for watching. Keep watching and stay tuned for more interesting videos. Have a good day.